So here's a pretty typical distance, rate, and time problem. And we're going to set this up as a system of equations. And there's a number of ways to do this. So I'm going to present this just using kind of a standard distance equals rate times time grid. So if we have distance is equal to rate times time, we're assuming that the rate stays the same. The rate is constant, it's not changing. Then we can set up a grid this way. We're basically comparing my two cyclists. I'll just call it cyclist 1 and cyclist 2. And it says that they leave towns 268 kilometers apart. So the most common mistake I often see is that students want to go ahead and put 268 in here for the distance of each cyclist. But if you think for a second where these two cyclists start, just think visually for a moment. It says that they are starting out, cyclists 1 and 2, 268 kilometers apart. So in reality, once they go and eventually meet, they're not actually traveling 268 kilometers. In fact, if you were to highlight, cyclist 1 here only traveled this little distance, much less than 268. And cyclist 2, you can see, traveled this distance. So it's the distances together add up to 268. So rather than putting 268 in each of my boxes for the distance, I have to think about this. I'll go ahead and say cyclist 1 traveled a distance of d. I'm not sure how far they traveled, but then cyclist 2 would travel 268 kilometers minus d, whatever the distance was that cyclist 1 traveled. So we would fill this in as 268 minus d. It says one cyclist is traveling 3 kilometers per hour slower than the other. So we can go ahead and say, I don't know what the rate of one cyclist is. Let's say it's just r. But then the other cyclist is traveling 3 kilometers per hour slower. So his rate would be r minus 3. And it says that they meet in 4 hours, meaning that they have both traveled for a total of 4 hours. So my time is going to be 4. So now you can go ahead and drag out your equation from each of these rows in your grid. We know that distance equals rate times time. So we have cyclist 1, their distance equation is distance is equal to 4 times r. And cyclist 2, their distance, which is 268, minus d, is equal to 4 times r minus 3. So we've created a system of equations that we can solve, and it turns out this one is set up to be solved by substitution because we already have the for top equation here solved for d. So using substitution, I can go ahead and substitute here my d value into my second equation. In other words, I'll end up with 268 minus my new d value, which is 4r, is equal to, and we could go ahead and distribute on the right-hand side, 4r minus 12. And then continuing to solve, we have 8r. I can go ahead and add 12 to the other side and have 280. And then we'll divide both sides by 8. So dividing by 8, I'll come up here just so we have enough room. Dividing by 8, 280 divided by 8 will be 35. So it looks like r is equal to 35. And then looking back at our grid, we see that r was right here. It was the first cyclist's speed, their rate. So the first cyclist is traveling 35 miles an hour. And then if I go ahead and take this value and substitute it into the rate for my second cyclist, which was r minus 3, then we can say 35 minus 3, because the second cyclist was traveling 3 kilometers per hour slower, the second cyclist is traveling 32 kilometers per hour. So it looks like the first cyclist is traveling 35 kilometers per hour, and my second cyclist is traveling 32 kilometers per hour. So again, this is just one way to set up this particular problem, what we consider a standard motion problem, and setting it up using the grid where we have distance is equal to rate times time. Not the only way, certainly, to solve this problem, but just one approach.